Magnetic Effects of Electric Current by Manjula Shivakumar from the Ashok Leyland School, Hosur, Tamil Nadu. Magnetic effects of electric current is a very interesting topic. In this, we will be learning about the relation between magnetism and electricity. Hans Christian Ørsted is a great scientist who played a lead role in helping us understand this relationship between the electricity and magnetism. Ørsted shows that electricity and magnetism are related to each other, which means if there is magnetism, we can create electricity, and if there is electricity, we can produce magnetism, and vice versa.
On completion of the lesson, students will be able to understand how electricity and magnetism are interrelated. Explain properties of magnetic field and field lines. Summarize the factors on which strength and direction of magnetic field depend. They will also be able to design various applications using electromagnets. Observe and appreciate the wide applications of electromagnets in day-to-day life. They also demonstrate curiosity in designing circuits and explore learning. They develop high level of reasoning and problem-solving ability. Analyze how electricity and magnetism work together. Finally, they apply theoretical knowledge in practical applications. Now let us see some of the interesting facts about how electromagnets are being used in our daily life. Electromagnets are used in computers, loudspeakers, the electromagnetic cranes to lift the scrap, televisions, copying machines, small toys, and many other appliances. Electromagnets has a wide range of applications in our day-to-day life. Now, let us learn about some of the electromagnetic properties by learning about the magnetic field and about the field lines. Moving further, let us learn about magnetic field and the properties of field lines. Magnetic field is the area surrounding the magnet where the effect of magnet is felt. When we place or suspend a magnet, it always shows north-south directions. The domains in the magnet are well arranged. That is the reason why they possess the property of attraction. The properties of magnetic field lines are: magnetic field lines are imaginary closed curves surrounding a magnet, which means you can see in the diagram there's a bar magnet, and if we sprinkle some iron filings around the bar magnet, the pattern of magnetic field lines is as shown. They are closed curves surrounding the magnet, and the flux lines is nothing but the strength of the magnetic field. The flux is very strong at the poles and weaker at the center. The magnetic lines is a closed imaginary curves surrounding the magnet. The second point is magnetic field lines emerge from the north and enter at the south pole. If you have to find out the direction of the magnetic field line, then a tangent drawn at that point gives the direction of the magnetic field line. Magnetic field lines, as depicted, are vector quantities which possess both magnitude and direction. The next property is no two magnetic field lines intersect each other, because if they intersect, they possess two directions, which is not possible. So if we place a magnetic compass also has a small magnet which deflects when it is kept near the magnet. So the magnetic compass helps us to show the direction of the magnetic field. After learning about magnetic field and the properties of magnetic field lines, let us learn about magnetic field due to current carrying conductor. Now in this activity, there is an arrangement where a copper wire is inserted from the center of the cardboard such that the plane of the cardboard is perpendicular to the copper wire. The two ends of the copper wire are connected to a source of battery, key and rheostat as shown in the diagram. Now, on passing current through the conductor, it starts behaving like a magnet. When we place a compass near the conductor, we will be able to see deflections, which shows that there is a magnetic field. To study the pattern of magnetic field, let us sprinkle some iron filings on the cardboard. The iron filings take the shape of concentric circles, which means the concentric circles says or shows that the field around the straight conductor is in the form of concentric circles and the flux or the field is stronger near to the conductor, and as we move away the field lines become weaker. If the current flows from north pole to south pole, the compass needle will deflect towards the east. And if the current flows from south to north, then the compass deflects towards the west. This can be remembered by the acronym SNOW, SNOW, which means when the current flows from south to north, the compass deflects towards the west and vice versa. Now, where do we see this application in our day-to-day life? So, we all know that we use credit cards in many places. So, when we swipe the credit card, we are actually swiftly moving the magnetic card across the machine. So, what happens? There is a change in the flux, which is actually generating some current and which is read by the card reader. The magnetic strip at the back of the credit card has some digital information about you imprinted on it. So, the magnetic card works on this principle of magnetic field due to current carrying conductor.
Right hand thumb rule. What is this right hand thumb rule? Right hand thumb rule is a convenient way to find the direction of current or the direction of magnetic field around the conductor. Imagine you're holding a current carrying conductor in your right hand such that the thumb points the direction of current. Then the four fingers wrapped around the conductor show the direction of the magnetic field. If the current flows from east to west, then the magnetic field around is in the anti-clockwise direction in the plane. And if the current flows from west to east, then the magnetic field is in the clockwise direction. So far we have learnt about the magnetic field around a straight conductor. Now in the slide, let us learn about magnetic field due to current through a circular loop. So let us do this activity where we take a circular wire or a copper wire in the form of a circle and it is inserted through a plane of paper from 2 points. Now let us connect the other 2 points of the copper wire to the source of the battery. Now on the plane of the paper, let us sprinkle some iron filings and gently tap on the cardboard. When the current passes through the circular loop, then it starts behaving like the magnet. And to study the field around the circular loop, the iron filings get aligned such that it is in the form of concentric circles near to the conductor, and as the radius increases at the center of the circular loop, it is in the form of a straight line. Proceeding
in this slide,
further,
we are going
after
to learn
learning
about
the magnetic field around the straight
current in a
conductor
solenoid.
and
So
circular
what is a
coil.
solenoid?
Now
First
let
of
us
all, what
learn
is meant
about
by a
magnetic
solenoid?
field due to
A
current in
solenoid
a
is
solenoid.
a long
What is a
insulated
solenoid?
copper wire
A solenoid
wound in a
is
form
a
of
long
a cylinder.
insulated
So you can
copper
see
wire
there's a long
which is wound in the
copper
form
wire
of a
which is
cylinder.
in the form of a string.
So
this
you can see in
copper
this picture
wire is in the
the
shape
length
of
of
a
the
cylinder.
solenoid
Okay?
is much
So the
greater
length
or
of this copper
bigger
wire is
than the
much
diameter
bigger
of
than
the
the diameter
solenoid.
of this copper wire.
Now
So
let
what
us perform
happens when
an activity to
this
study the
solenoid
magnetic
is
field
connected
around the
to a
solenoid.
source of battery? When an
Let the
electric
solenoid
current
be
is passed through a
connected to a source
solenoid,
of the
the
battery.
magnetic field is
When the current passes
produced
through the
around
solenoid, it
We have
starts
learnt it
behaving
earlier
like
that
a magnet.
all passing current
So
through
the
a
point
conductor
where the
starts
current
behaving
enters the
like
solenoid
a magnet,
behaves
and
like
the
the south
solenoid
pole,
is also a
and the
conductor,
point where the
but the
current
shape of
leaves
it is
the
just
solenoid
like a string. Okay?
that side
So,
behaves like the
when the
north
current
pole.
is passing through the solenoid,
So
it
if you
starts
see
behaving
the
like
pattern
a magnet,
of
and
magnetic
the field,
field
so
around
the
the
pattern of
solenoid,
magnetic field
it
so
is
formed
similar to that
is
of a
as
bar
shown in the
magnet.
diagram below.
So
if you
the
compare
field
the
around the bar
magnetic
magnet
field pattern
and the
of a
field
bar
around the
magnet
solenoid
and
are
that
similar.
of a solenoid, both
Solenoids are
similar.
widely used
So
in
the
various
pattern of
appliances in
magnetic
our
field
day-to-day
lines
life.
around a bar
Since
magnet
they are used
and the
in
pattern of magnetic
unidirectional
field
function,
lines around
they are
a
used as
solenoid
power
are
switches
similar. So the
in the
point
valves
at
which are used in the washing
current
machines.
enters the
The
solenoid,
inlet valves
that
allow the
point
water only in
becomes
one
or
direction.
starts behaving like
They are
a
also
south
used
pole.
in the
And the
credit
point
cards.
from where
The
the
magnetic
current is
strip in the
leaving
credit
the wire,
cards
that
use the
point
solenoid
becomes the north
to
pole.
write
Okay?
information
So if you
in the
see
form
in
of
this
digital
diagram,
information.
the field lines
it is
are
printed
shown
on
with
the
the diagram,
credit card.
and the points
So the
where
solenoids
the
have
field
wide
lines
use
where
in our
they are
day-to-day
entering
life.
the solenoid, that becomes the south pole, and the point where the place where the field lines are emerging out of the solenoid becomes the north pole. So if you see the solenoid, the pattern of magnetic field around the solenoid and the pattern of magnetic field around the bar magnet are similar.
In the earlier slides, we have learned that when electric current is passed through a conductor, it starts behaving like a magnet. Now let us study about how this magnet, electromagnet, behaves when it is brought near a permanent magnet. So in this activity, we have an aluminum rod AB which is suspended with the help of a wire, and the wires are connected to the source of battery and a key. A permanent horseshoe magnet is placed perpendicularly to the aluminum rod such that the north pole is below and the south pole is above the aluminum rod. Now when the current is passing through the circuit, the aluminum rod gets magnetized and starts behaving like a magnet. And the force of the horseshoe magnet and the electromagnet interfere with each other, and because of which the rod experiences a force. When we reverse the direction of the current, then the deflection of the rod will be in the opposite direction. Thus, if a current carrying wire is placed in the magnetic field, then force acts on the wire. As the direction of current is reversed, the magnetic force also gets reversed. The same logic is used in designing of the electric bells.
After learning something about magnetism and electricity in this chapter, Magnetic Effects of Electric Current, I would like to ask you to try these two activities as a part of experiential learning. The first activity is to make a magnetic compass, where you have to take a foam sheet and cut it in the shape of an arrowhead as shown. Next, take a ring magnet, only half of the ring magnet, and place it such that the north of the magnet faces to the arrowhead. And then place this arrangement on top of the water and observe. It shows north-south directions and acts perfectly like a magnetic compass. Next activity is to make an electromagnet. Take a copper wire and wind it around an iron nail and connect it to the source of battery. Now after some time, bring some paper clips or small iron nails and observe what happens. Current gets induced into the nail and it starts behaving like a magnet. And the iron nail attracts the other paper clips or nails. This shows that the iron nail behaves like a magnet on passing current through it. This is the effect of electromagnetism. The same principle is used in electric cranes to lift up the scrap. When the current is switched off, it loses its magnetism. So thank you. I think you all have enjoyed the session.